All right, the second example is slightly different. In this case, somebody stands on a building and chucks a rock. So if you're standing on a building that is 10 meters high and you chuck a rock, it's going to go up, 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 and then down, 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 and hit the ground. So this problem is slightly different. So if I impose a coordinate system, the most obvious one is to go like this. That's going to be y, and that's going to be x. And we are starting 10 meters up, 10.0 meters. That's how high we're starting. Okay? We know that the initial velocity of the projectile is 12.0 meters per second, and the launch angle is 18.0 degrees. So it's thrown at a fairly shallow angle. Okay, it's not too steep. The variable list, forgot to stamp it. We have delta x, velocity in the x initial, velocity in the x final. What's the acceleration in the x? 0. We have the time. And for the y direction, delta y, we have the velocity in the y direction initial, velocity in the y direction final, acceleration in the y direction, which is negative g, and the time. So there we go. All right. Same thing we did before. We are going to start by finding the components of the velocity in the x and y direction. So you ready, Max? Step 1, we are going to find the velocity in the x direction initial, which equals the initial velocity times the cosine of the theta. What do you got, Max? Close your computers there. What do you got? Come on, Max, I gave you a warning. And we are going to find, while he's doing that, velocity in the y direction initial, which is v0 sine theta.
114.
Which one?
For the first one.
It's what?
114.
I don't think so. 12 times the cosine of 18.
12. I thought that was 120.
12 times the cosine of 18.
11.4.
11.4 meters per second is how fast it's moving horizontally. And vertically? Got it there, Elise?
3.7.
3.7.
08.
Okay. 0.8, just so we don't round too much. All right, now step 3. We've got to find time using delta y equals velocity in the y direction initial times the time plus 1/2 the acceleration in the y times the time squared. But now, you don't get a freebie. A, B, and C in the quadratic are all non-zero. So you're going to have to solve the quadratic. Okay? So at this point, I'm going to relax my algebraic solution requirement. If you have to solve the quadratic, you don't need to solve it algebraically. Let's write out what it means. What's delta y? Oops, let's go back here. What's delta y? Is it 10 or negative 10? Did it end up 10 meters above where it started or 10 meters below where it started? Below. It actually ended up going down. So this is negative 10 meters. Okay? So we also know the velocity in the x direction is 11.4, and the velocity in the y direction is 3.708. So we found those already, right? All right, so this is going to be negative 10 equals the velocity in the y direction initial, which is 3.708 times the time, plus 1/2 the acceleration in the y direction, which is negative 4.905, right? 1/2 of g is 4.905, and it's downwards negative. So that is the equation we're solving now, right? Put it in standard form. 0 equals 10 plus 3.708t minus 4.905 t squared. And once you have it in standard form, the solutions will be minus b 3.708 plus or minus the square root of b squared 3.708 squared minus 4 times negative 4.905 times c, which is 10, all over 2 times negative 4.905. That is going to be our solution. And you don't need to do that algebraically, okay? You can do that numerically. You can do it algebraically. You're just going to have V0 sine theta here, V0 sine theta, 1/2 of G delta y, right? It gets a little ugly. Students tend to get frustrated when that happens. So those are your two solutions. Stick them in your calculator, and hopefully you've had some practice from yesterday. You can crank out the solutions. Go ahead and list both of them, please. So, let's see. Kennedy, we picked on you yet? We have? Darn. Maddie, you got one of them? We're working on it. Trinity, you cranking up one? Which one do you have? Okay, keep going. You got an answer there, Mr. Peterson?
So it could either be negative 1.1, I think, because I just put the variables in, and I just solved on the quadratic function.
Yeah, I can't remember what the solutions are. Negative what?
1.1.
Yeah, like negative 1.099?
Yeah.
Yep. And who else had one? Was that the one you were doing, Trinity?
Yeah.
Negative 1.099 is one solution. You got the other one, Maddie?
I think it's 1.855.
1.55?
No, 1.85.
1.85, that sounds about right. 1.85. And those are all in seconds, okay? So I want you to show me this is what you're doing. This is how you do it. And these are your solutions. List both of them. Now, which solution are you going to choose? The second one, because it's positive. What does this solution mean? Does it have any meaning at all? It actually does. So we started our clock, t equals 0, when we threw the ball, or the rock, right here. We threw it that way, right? And we are asking, at what time is delta y negative 10? At what time is it on the ground? One possible answer is 1.85 seconds after we throw it. Goes up and hits the ground. But another possible solution is a projection backwards in time. If you imagine going backwards in time, this projectile could have come from here, past that point and hit the ground, right? And when would it have been on the ground backwards in time? 1.099 seconds before it reached this point. So the negative solution actually has meaning. You can think about what it means, but it's not the one we're going to choose, okay? So in mathematics, we would say it's extraneous. But it still has, I mean, it's kind of cool to think about, okay, backwards in time, that's when the rock would have been on the ground also. All right, so that's our solution. And so now we can't get an algebraic solution because we don't have an algebraic solution here, but we are just going to evaluate the range equals the velocity in the x direction initial times the time plus 1/2 the acceleration in the x times the time squared. That, of course, is 0. And so just plug in your velocity in the x direction initial, which is 11.4. Hopefully you got it there without rounding, right? Times the time, 1.85, which you have without rounding. And all of that gives you a range for the rock of, anybody? 21 point what? 21.1, is that okay? I'll go with 3 significant figures, meters. So there we go. We solved the general projectile problem. Okay? So if your coefficients aren't all 0, you can solve it algebraically. If A is 0, or if B is 0, or if C is 0, you can find it in an algebraic solution. But if they're all non-zero, you're going to have to solve with a quadratic equation. And if you are frustrated solving this and you just can't get the answer, and you use a tool like an online calculator, or maybe you got quad form on your calculator, I don't care, that's okay. I still want you to write the equation you would be solving if you could. So show the equation so I can see that you understand where the coefficients go. Try to do this, keep practicing. Evaluating complex expressions is a skill that you can build, okay? So try it a couple times. Let me help you if you're here, but if you're home and it's late and you're frustrated, grab a calculator, an online calculator, plug in C, B, and A for the quadratic formula to help you along, okay? But it's a crutch. As long as you know it's a crutch and you gotta wean yourself out of it, that's okay. All right? Okay, so that ends the unit. You've got some problems to solve. If you get them all done, there's some really fun bonus problems to do. And that's it. So you got about 35 minutes now. And we're gonna move on to momentum. We're not gonna take time to have a test on this. Sorry. Please make me nice solutions though. Since I don't have a test, the only way I can evaluate what you're doing is your solutions. So start with the diagram, make a variable list, clearly list your plan, show what you're doing. I'll leave that up there.